second subspace of magnificence is the null space of A, right? It's getting serious, people. Okay, so this is just going to be an introduction to it, and in the next piece we'll talk about how to find the null space of A and the column space of A. But there are a couple of things, so we're going to define the null space of A first, right? Okay, let's get that into our heads. And then connect it to AX equals B, which, as you know, is everything in life, really. Okay, so column space of A and null space of A, what do they mean? And you know, I'm not going to write column space of A all the time. I'm going to put C of whatever the blob is and N of whatever the blob is for column space of A and null space of A. All right. So it's really simple, and it turns out that there's a particular AX equals B that's super important. It's the case when B equals 0. So the null space of A, all right, so let's just think about this. So consider, I've got the wrong thing switched on. So consider AX equals B. AX equals B when B is 0, so AX equals 0. Very special equation. So which combinations of the columns of A give you 0? Right, this very special B. So this is about how do we combine the columns to get to do nothing. And what we'll see is that you have to accommodate this, because when you find a solution to a AX equals B when B is non-zero, you can always add this solution. So all right, we'll get that. Sometimes you'll see this written as, right, this is called the, we'll call it the null space problem, right? The null space equation. Let me say it like this. You'll also see the homogeneous equation, or homogeneous equation. I mean, these are antiquated terms. That you'll see that in differential equations as well. When the differential equation is set up on the right, and if it equals 0, that's a homogeneous version. If there's some sort of forcing term over here, non-homogeneous. Okay, because we don't say heterogeneous. Okay, exciting. The monks push us forward. So the question is here, yeah. So the question we're asking is, how can we combine the columns of A to produce nothing? So if we think about the columns being musical notes, let's do that, right? And you want to play a sound. So there are some ways apparently here where musical notes can cancel each other out, give you no sound, right? This is just, yeah, I mean, it'll have a very mathematical feel to it, but there's a sort of a deeper story that we'll get to eventually. So, can you think of a solution? So an immediate observation is that x equals 0 works, all right? A times 0 equals 0. So there's always a solution here, actually. So there's always a solution. And if we go back to thinking about column space, we had this idea that there's only a solution to AX equals B if B is in the column space of A. The column space of A is a subspace of Rm, and 0 is always in the subspace, right? One of our big rules. Three rules. Yeah, 0 is always in a subspace. This is an addition that I'm not really sure we need to do, but it's there. Okay, so I'll get rid of that. I've added all sorts of things that I need to unsquiggle. Okay, good. All right. We're very excited about this. So 0 always works. Let's think of an example. Okay, so this is a start. Always a solution. There's always at least a solution. Maybe one or infinitely many. Still an AX equals B problem. We know all about these, in principle. Infinitely many. Wow. This is really, it's really going to take off, people. This is great. Beautiful, beautiful stuff. So, one or infinitely many, and let me just add in here that 0 is an element of the column space of A always. Well, it's a little bit dense in there, but okay, fine. Okay, so an example. And this is one where I'll just tell you some solutions. We're not going to grind our way through it. It will be row operations again, right? Right? Bigger things, but the stuff we learn at the start of the course will matter all the way through. The rest of your lives. Okay. A equals, it's good, it's a beautiful, beautiful area. So let's try this one. 1, 2, 3. You can see we're just making this up. 1 minus 3 minus 2, 0, 1, 1. And for the case, again, right, B equals 0. So we're solving, this is us, right? Solve AX equals 0 for this. And usually there should be, let me annotate this properly. So, right, pain and suffering. Right, these things are here, right? Row reductions, we do it, right? Yep. Solve, right? Solve. Row ups. So we go all the way through, we do back substitution, whatever we like. And we end up, so let me just say we can, pain goes on. We can see, here's one solution. X equals C 1 minus 1. Where C can be anything. Now, well, it's possible there are more solutions, but this is actually it. Okay, in this case. So we obtain this, and if we look at this, let's see how it works. So first column plus the second column minus the third. So there it is. First column plus the second column. Let's just do that. So we have 3 minus 2 and a 1. 3 minus 2 and a 1. So if we're going to subtract the third column away from the sum of the first two, then it works. All right, good. So we can see this is a good thing. Okay, fine. So this gives us 0. Gives us AX equals 0. So we could call it, okay, so let's do this. We'll say, I'm gonna sort of just jump a little bit. The null space of A is equal to, in this case, right, just for this example, is X in R3, right? This is a 3 by 3, and this is M, and this is N. And where does X live? Actually, X lives in Rn, right? It's the number of columns, right? The length of X is the number of columns. So this is N. In general, it's a 3 by 3. We'll soon get to a 3 by 4, which will give us some more examples. Why did I do that? Okay. Good. So it's any X in 3 such that, we can just simply write this. X, but we have to give it the nice curly brackets. X equals C, 1, 1, minus 1. C is an element of R. Okay, that's the null space. So this is the null space of A. So it's, again, all the x's for which A times X equals 0. Right. So why does that matter? You'll see this notation. So notation is sometimes, and I'm going to leave out a kind of a funny, an alternate one. I'll mention it. We'll put xn for a null space vector. Maybe I didn't say this quite properly, but this is clearly a subspace of R3. Right? It has a 0, right? It goes through 0 and it traces out a line in 3 dimensions. Very important. Very important. So this is a big deal. So the null space, just like the column space, is always a subspace. Okay. Sometimes also you'll see this. You'll see X, H, and this is homogeneous. I just want you to know that that's an alternate formulation. We'll avoid that language mostly from now on, right? So that's important. So a little bit of notation. And okay, fine. So we'll have it a little bit, but I'll just try, quickly as possible switch to xn for null space because that's what we want to think about. Okay, so let's imagine we've got the same A. We're not solving. So now, right? Now solve. So we know this thing about the null space. So now solve A, X, and I'll put it in properly. So this is 1, 1, 0, 2, minus 3, 1, 3, minus 2, 1, times X. Well, let's put it all in. This is X1, X2, X3. These things just, they don't do themselves. It's unfortunate. Okay, so we've got this, and let's put a problem in here that's not a 4 minus 1, 1. Right, so a non-zero B. Non-zero interesting B. Right, huge. Okay, so again, we've got the suffering. Imagine the suffering. So so suffering, more pain and suffering. This happens, right? I encourage you to do it. You don't have to, but let's imagine there's more pain and suffering, also known as row operations. Yes. Right. And pain and suffering, you should watch the Barclay Marathons. That is an incredible movie about pain and suffering of a particular kind. Okay, so let's see. So we would work through this problem, Ax equals B, and we would find X. So we would find X equals, yeah, look at that. Yeah, so if you look at this, you can see, this is not how you solve it, of course, you're going to do row operations. If you add row 1 to row 3, you get the final one. It's very contrived, right? So 1, and then we want 0 of the second row, second column. So second row, first column plus the third column is equal to B. Right. So we want 1 of the first column, 0 of the second column, 1 of the third column. Words. So we see this works. So, but actually it's through pain and suffering. All right. But I'm just showing you that this is true. So you'll see this called, so this is sometimes called, could be called, and this again fits with differential equations a little bit, XP, where P is particular. Again, this is old language, but it means it's a solution that does the job. It gives you A times this thing gives you B. I should label it as B. And I'm just going to call it X sub R though, for some reason. Okay. We'll write X sub R because the monks said so. Because some dying monks said, we should, right? Usual thing. Mysterious, strange monk. Okay, so we're like, okay, guy. So wrong. All right, so we're going to write X sub R. So we know, so we have A X N equals 0. That's this null one. And A times XR, so let me put it in here, R, A times XR equals this B, equals 4 minus 1, 1. This is our B, right? Our interesting B. So the issue is this isn't the only solution. So we see XR, and this is the right thing, is not a unique solution. Because A times XR, right, plus XN, that's a bad, let's make this bigger, plus XN also equals 0. So I'll do this on the next thing, right? So equals, not 0, equals, I'm jumping a little bit, let me write it properly, equals B, right, equals this B. All right, so let's do that, I think I want to do it by actually writing it out. Okay. More. Right, here's our A. 1, 1, 0, 2, minus 3, 1, 3, minus 2, 1. That's our A. Stop the yelling and being too excited. Just calm down. It's going to be okay. So we've got this A, and we're going to add these two pieces together. We're going to say, all right, 1, 0, 1, plus any multiple, very excitingly, of 1, 1, minus 1. Interesting. Let's see what happens. Let's see what happens with this. So this is our A. Right, this is our A. This is what we said was XR, because of the monks. And then this whole thing here is any of these X null vectors. Right, so we multiply the whole thing out. I'm just going to do the whole thing. I think it's all right. 0, 1, 1. 1, 0, 1. Right, that's A times XR plus. So let's point these things. Boom, a boom. Important mathematical technique with the booms. 1 minus 3 minus 2, 0, 1, 1. And then that constant C, it's just a constant, right? So we can, let me pull it out the front. Goes to here. That's technically how it moves. You go. Okay. Okay, so this is now A, and this is, yeah, right? Well, this whole thing here is 0. That's what that null vector does, 0, 0, 0. This whole thing does our work. It's the one that gives us B, right? B was 1, 4 minus 1, 1, plus this, right? So we add these two things together, 4 minus 1, 1, which equals B. So the deal is you can always add to this special solution, this XR, we can always add a null vector, and if the null vectors, this is a point, if the null vectors exist, if there's more than just 0, because 0 always works, then there are always infinitely many solutions, right? If there are any null vectors at all, there'll be infinitely many, because you're solving AX equals 0. If you get any non-zero solutions, we know there are infinitely many. Think about that a little bit. So there are, in fact, let me write it like this. There are infinitely many solutions because the null space of A is not equal to just a 0. Plenty of matrices with a null space of A is 0, right? A times 0 equals 0. But it's not that. There are a whole bunch of crazy things we can throw in here that just get annihilated, they get wiped out by A. So we can always take our solution, add something to it that gets cancelled out. So if our A's columns were notes, there's one arrangement that makes the note we're trying to make. That's our B. And then there are all these other arrangements we can put together that cancel out. That seems like they shouldn't be interesting, but they are actually a valuable part of the solution. Okay. Okay, so the big deal. The big deal here, again, a technical mathematical concept, right? Theorems, lemmas, corollaries, big deals, is that, and do I have this properly here? Okay, so maybe just let me write it like this, down here. Okay, let me write this too. So A times XR, I didn't quite have this on the previous page, XN, if we multiply this, equals A, it's what we just did with this one example, but I'll just do it in general. So in general, and then we'll just spread them out, AXN. This part is 0, right? That's what the null vector does. And this one is B, right? Does the work. Okay, good. But we cannot discard these other ones. Okay, so we know what the null space of A is. It's all the x's, A times x equals 0. You can see that it's, okay, so let me just say that again a little bit. You know that it's a subspace because any two vectors that satisfy A times x equals 0, you can add them together. That's still true, right? The sum, it's still true. The multiple, it's still true. And 0 is in there, right? Big deal. So there might be more than one. So 1, the big deals. So 1 is that all vectors for which AX equals 0. I guess I should say it's fallen apart. Okay. All vectors x, and they live in Rn, right? The number of columns of A, for which AX equals 0, form a subspace of Rn. Right? Basic properties are, I think, subspace property 1. So A times x1 plus x2 equals A times x, right? So we've added them together. Of course, we can do this. So if they both have the property that this is 0 and this is 0, then the sum has that property 0. So that's that one. Subspace property 2. A times C times, see, this is kind of silly, but it's just a constant, so you can pull it out. I don't know what happened to my voice. And then we've got this, and A times X is 0 because it's in the null space. So it's C times 0, which is just 0, right? So very important, the little, it's a 0 vector, not the 0 number. Property 3 is 0 is in the null space of A because A times 0 equals 0. Great. So it's 1, big deal. And then 2, I'll just call this thing 2. So this is where we start to get some power. And this is all I want to say in this section. So if the null space of A equals 0, there's nothing interesting in the null space. A times 0 only has one solution. And B is in the column space of A. We can make it. then AX equals B has one solution. Has one unique solution. There's only one way to do it, and it exists. So there's that part. Now, this is what the null space does. Okay, so and if the null space of A is not equal to 0, right, and B is in the column space, let me put that on a new line. B is in the column space of A, then AX equals B has infinitely many solutions. We're going to see this, it's going to come out, but this is the big deal. Infinitely many solutions. The next piece is about finding null space and column space. And lastly, if it doesn't matter what the null space is, right? If the B is not in the column space of A, let me write that better, column space of A, then AX equals B has no solutions. No solutions. We'll have a nice table for this later on, and it's a table you should be able to fill out. It's very readable. Okay, so 3 things here. No solutions, infinitely many solutions, one unique solution. And these are the, so, you know, this is just a completely different story now. We're talking about subspaces, we're talking about where the B's live, we're talking about things about the X's, so the null spaces are all about the X's. All right, super important. Let's start to let that kind of seep into your minds and let the happiness just slowly build, okay? All right, so as I said, we have 2 subspaces now. We have to figure out how to find them for an arbitrary matrix, because clearly that's what everyone would be requesting at this point. And then there will be 2 others. They all turn out to be mirrors of sorts. So as so often happens, we've already done the hard work, but okay. We're going to figure out 3 ways eventually to get column space, kind of one main way to get null space, and the others will come as well. All right, all is coming.